So let's discuss scenario 3 here. You can see that in scenario 3 we have two different classes, but one data point of this class is lying here, which is very close to this class. And we have two hyperplane hairs, one is wave A, one is B, and we need to select that which hyperplane is the best hyperplane for this kind of problem. So if I ask you to decide that which hyperplane is the best hyperplane depending upon our previous knowledge, so most of you will say that this hyperplane B will be a good choice because by observation I can see that the hyperplane B seems a good choice because the reason is that it has a higher margin as compared to A, right? So right till far we have discussed that we need to select a hyperplane that has higher margins here. So it seems that B has a higher margin as compared to A, but it's in reality, in case of support vector machines, it is a little bit different. So the catch here is that the SVM selects the hyperplane which classifies the classes accurately prior to maximizing margin, right? So in case of SVM, so the SVM will select the hyperplane A because it is giving importance right now to the classifications, because the hyperplane B is basically misclassifying this data point here. So that's why the hyperplane selected by the SVM will be A because it performs this selection prior to maximizing this margin. So here the hyperplane B has a classification error because this hyperplane will be misclassified, will misclassify this data point here, and the A hyperplane A will be able to classify it correctly to this class. Therefore, here we can see that the right hyperplane will be A. Now in scenario 4, things are a little bit complex. You can see that we have a data point which is almost in our own class. So this data point can be some kind of noise, or it may be an outlier, but it happens to be residing in this class. So below, I am unable to segregate the two classes using a straight line. If I draw a hyperplane, no matter in which direction or how many hyperplanes I have here, it will be very difficult to segregate the two classes because of this outlier here. So as one of the stars which is from this class lies in the territory of these circles here. Sorry. Now, as I have already mentioned, one star at other end is like an outlier for star class. The SVR algorithm has a feature to ignore outliers and find the hyperplane that has the maximum margin. So the support vector machine algorithm has the capability through which it can ignore the outliers. So in this case, this is the outlier, so a support vector machine can draw a decision boundary by ignoring this outlier, and it can find the right hyperplane having the maximum margin. So we can say that the support vector machine classifier is robust to outliers. It means that it is not being affected very much by the noisy components or the outliers. So it is robust to outliers. So let's now define the technical key terms or key points of a support vector machine. So let's start it from the support vectors. Let's see what are support vector points in a support vector machine. The vector points closest to the hyperplane are known as the support vector points because only these 2 points are contributing to the result of the algorithm. Other points are not. So I will say that only those instances or only those data points will be support vector points for my SVM which are very close to the hyperplane. So all those points which are close to the hyperplane will be considered as the support vector points. Why? Because only these vector points are playing a role or contributing to the result of the classification, and the other points which are far away from the hyperplane, they are not playing any role in the classification. So we will say that the support vectors are only those points which are close to our hyperplane. If a data point is not a support vector, removing it has no effect on the model, because the points which are away from the hyperplane are not contributing or are not playing any role in the classification. That's why even if I remove those data points which are not support vectors and they are away from the hyperplane, my end result will be the same, or the removal of these points will have no impact on the model itself. On the other hand, deleting the support vectors will then change the position of the hyperplane. So because the support vectors are playing a role in the decision boundary, so if I remove or if I delete the support vectors, then I will have a difference in the classification, or I will say that my decision boundary will be changed accordingly, because then I will have new support vectors and my decision boundary will be according to those new support vectors. So in this figure you can see the differences between normal points and the points which are support vector points. So we have a hyperplane here, right? And we have two further hyperplanes, which one is negative hyperplane and one is positive hyperplane, because one is for the one category of the data and the other one is on the other side of the data. So I can say that this middle one is a hyperplane which has a maximum margin from all the support vectors, and these two other hyperplanes can be considered as one as a negative hyperplane and the other as a positive hyperplane. But the maximum margin or the maximum margin classifier will be only this middle hyperplane here. So I can say that the data points which are close to this maximum margin hyperplane are my support vector points. So in this case, this point and this point will be my support vector points, as they are close to the hyperplane, and these other points are not my support points. So if I remove these 2 points, for example, or if I remove these 2 points from here, you will see that there will be no effect on this hyperplane. But on the other hand, if I remove this point from here and this point from here, you will see that my my decision boundary will move from right or left, because then the new support vector might become this one or this one, and the position of my decision boundary will change accordingly. So what is a hyperplane? The dimension of the hyperplane depends upon the number of features. If the number of input features is 2, then the hyperplane is just a line, as we have seen in all the figures right now. If we have data points or features in a 2-dimensional space, then our hyperplane will be just a single line. If the number of input features is 3, so now if I increase the dimension of the features and I have the third dimension, then the hyperplane will become a 2-dimensional plane, right? Because now I have 2-dimensional, and in the 2-dimensional plane, I will call my hyperplane as a 2-dimensional plane. It becomes difficult to imagine when the number of features exceeds 3. So if I have more dimensions, then obviously we will be unable to imagine more dimensions. So if you see in this figure, I have support vectors and I have my hyperplanes here. So this is the case of 2 dimensions, right? So in 2 dimensions R2, I have my hyperplane as a line here, and this hyperplane is basically classifying these 2 sets of data. But in a 3-dimensional space in R3, my hyperplane will become a plane here, right, like this one. So these are basically the 2 terminologies which are being used for hyperplanes in 2 or 3 dimensions. Now, what is a margin? As I have explained earlier, that margin is the distance of the support vectors to the hyperplane, right? So it's a distance from the instance or data point to the separating line. We would like to choose a hyperplane that maximizes the margin between classes. So the key point is that we want to select a hyperplane which can have maximum margin from data point to the hyperplane. The graph in next slide shows what good margin and bad margins here. So let's see in this figure that what are good margins and what are bad margins.